Chemistry chapter 24, theory video 8. Stability constants is what we are going to learn. Now you know that the stability of ligand replacement, that is after the ligands have been replaced, then the product is going to be more stable than the original. That is something that we learned earlier. Now, when the aqueous solutions of transition elements are hydrated, that means they make complexes with water molecules. That means the water molecules act as ligands by forming dative or coordinate bonds with the central metal ion. So the different ligands, that means by depending on how many water molecules are there or what other types of ligands are there, their stabilities are going to be different as well. Now, when you add concentrated aqueous ammonia to ammonia to copper to sulfate, ammonia will be displaced. Ammonia will actually displace water ligands in a stepwise process. That is what we learned earlier. So, in a simple sense, what happens is initially copper and water ligand complex will join up with ammonia to produce, one by one the ammonia will get replaced. So as you can see here in the first equation, one ammonia is getting added, then in the second one another one. So that means there would be two ammonia ligands attached, replacing or rather displacing water. So when we keep on increasing the concentration of ammonia, it will proceed until 4 of the water molecules are replaced by ammonia molecules. So as a result, you will get a deep blue solution which has CuNH3,4 H2O2. That is going to be the deep blue solution. And that is going to be the overall ligand substitution reaction. So what happens is here, now the competing equilibria, that means the equilibrium will lie towards in the direction of the more stable complex. Now the more stable complex in this situation is the product, because it is more stable than having only water as ligands. So then what happens is, if you add more water to this, that is, if we add more water to this, then what happens is the equilibrium will have to shift to the left to add more water molecules to as ligands to the ion. That is because it opposes the changes that happens. So that is something that you need to understand. So then, just like the Kc that we learned earlier, we have another equilibrium constant that we deal with here. This equilibrium constant for ligand displacement is known as stability constant, K-stab. But we usually write it for the overall reaction rather than stepwise. And it is the same as for Kc. So here, copper and water ligand complex, when replaced with the chloride complex, you get CuCl4 2- plus water. So the products are CuCl4 2- aqueous. So obviously we don't consider water, divided by copper H2O complex plus Cl- complex, Cl- ions. The reason why we don't add water is because water is in very large amount, that it is concentration is considered to be constant. Then the units are going to be considered in the same way as Kc, you know that, and it is not something that is confusing because we have discussed this many times over. Stability constants, we can actually give these values in to the base log 10 scale, and then when given in log 10 scale, they don't have units, and they can be used to compare the stability of any two ligands or many ligands. Higher the stability constant, more stable the complex is going to be. Now, for example, chloride ions have a K-stab value of 5.6, that is to the base 10, log to the base 10. Then ammonia would have the same value. Ammonia would have 13.1 as K-stab. So then that means more than the chloride ligand complex, ammonia complex is going to be more stable. Then hydroxybenzoate 16.9, dihydroxybenzene, it is 25, as you can see here. Now you can see that chloride, ammonia, they are all monodentate ligands. Here the CO2OH, they are bidentate ligands. You can see them. Now bidentate ions, that means now, for example, here 2-hydroxybenzoate and 1,2-dihydroxybenzene, they have higher stability constants than monodentate ligands. So then to understand what would happen if different ligands are added to complex ions, we can figure out what would happen. Now we know that excess ammonia, if we add excess ammonia to the CuCl4 complex, it should result in the production of a ammonia complex. Why? Because the stability constant of ammonia complex is more than the chloride complex. So that means the position of equilibrium is going to be shifted in the direction of the more stable complex. As a result, you will get the forward reaction to take place. Now, if you add excess of 1,2-dihydroxybenzene to the dark blue ammonia complex, so that would produce the green complex of 1,2-dihydroxybenzene, because it has a stability constant more than ammonia. So so what happens is, if this is added, because it is actually very much powerful, that is, if you add the dihydroxybenzene 25, that actually would means the copper complex is actually, because these are powers that we are talking about, it is very much more stable than the ammonia complex. As a result, if you add this chemical, the dihydroxybenzene chemical, you will get a mixture which would have hardly any amount of ammonia complex. So that is actually, you have, because when you talk about the logarithm to the base 10, that means you are actually talking about a power. So that means it is going to be more, when you divide it compared to the actual values, the ammonia's stability constant would have to be raised by a power of 13.1 to reach the stability constant of the 1,2-dihydroxybenzene complex. So that means it is very much more stable than the others. So you would understand that that complex, ammonia complex, will break down into produce the 1,2-dihydroxybenzene bidentate complex. Now let's look at this worked example. When concentrated hydrochloric acid is added to copper 2 sulfate solution, the aqueous solution formed contains CuCl4 2- and CuH2O4 2+ complex ions. Write the expression for stability constant for CuCl4 2- in an aqueous solution. First, what we are going to do is, we have to write the chemical equation for the ligand exchange equilibrium. So CuH2O4 2+, plus 4Cl minus gives you CuCl4 2 minus aqueous plus 4H2O. So that is what is going to be produced. Then we write the K stability constant equation K stab. So the products over reactants CuCl4 2 minus aqueous over CuH2O6 plus Cl minus. Then from that we have to figure out K stab units. That is going to be mole per cubic decimeter divided by mole per cubic decimeter, mole per cubic decimeter. So then it is going to be dm to the power 12 mole minus 4. Mole minus 4 because the concentration of Cl minus is to the power 4. I hope you understand that. Now using table 24.4 explain the proportions of the two copper 2 complex ions present in the equilibrium mixture. Now in the table, if you look at the table, the stability constant for chloride ions to the base 10 would be 5.6. Now that means actually the actual value is raised to the power of 5.6 when in comparison to water. So that means the concentration of products in equilibrium expression CuCl4 minus is going to be very much greater than the concentration of copper and water ligand complex. Then they are asking what would happen if concentrated ammonia solution is added to copper 2 chloride solution. So that means when you compare the K stab value for copper 2 complex with ammonia is very much higher than the chloride ions. Then it produces a very much more stable complex CuNH3 4 H2O2 plus, and it is it is going to convert the chloride complex into a deep yellow chloride complex into a deep blue color, right? So that is, the ammonia complex is going to be produced. The exchange of ligands occurs step by step as successive ligands are replaced. For example, the second step in the exchange of water ligands for chloride ion ligands is shown by this equation. So first one chloride ion has been added, then the second one is going to added, replacing a water. It was found for this reaction that when 0.15 mole per cubic decimeter solution of the complex ion CuH2O5 Cl minus was Cl plus was mixed with 0.15 mole hydrochloric acid, the equilibrium concentration of CuH2O4 Cl2 complex was 0.1. Write an expression. So the details have been given and they will ask you other questions. So the stability constant equation is CuH2O4 Cl2, that is the product, over the reactants are CuH2O5 Cl, then Cl minus. Then they ask for calculate the K stab values for the reaction given the units. So they have given at start the values would be given. Initially there was no copper and Cl2 complex, there was none. Then at equilibrium they have given what is being produced. So the difference of that is going to be left at the end. Then you find the K stab values using the values that they have provided. I hope you understood. If you understood, you will have to go to question number 6, but before that let's write down a note. If you didn't understand, please ask questions. Write down stability constants. Different ligands form complexes with different stabilities. This expressed in terms of equilibrium constant for ligand displacement will be known as stability constant, K stab. It is written in the same way as Kc. Please write this down. And its units are calculated in the same manner. Put a star and write down. The higher the value of stability constant, more stable the complex is going to be. When the stability constant is very much higher than another complex, the more stable complex is going to be produced in larger concentrations. I hope you understood. Please do question number 6.